Hey folks, okay, so I wanted to make this really quick, hopefully very quick. I'm gonna try to be brief. We know that might not happen, but I'm gonna try. Video just going over a couple questions that people had asked me to go over in regards to quizzes. And additionally, I had a problem or two from 12.4 that I wanted to look at just really, really quickly because they were stuff that is important that I think you should know that I didn't go over on Tuesday's discussion. So first and foremost, I got a request in for problem 2 from quiz 16. So I wanted to go over that one really quick. It is possible that you guys had a slightly different problem because we can take variations here. But this was one of the options that I saw was problem 69 from 12.1. So that's the one we're going to look at. So we have integral of x squared e to the x minus 2x all over x squared. Now remember, same as with derivatives, if we don't have something that looks exactly like one of our derivative rules, then we have to manipulate it. Same thing is true with our integrals. If we don't have something that looks exactly like our three integral rules that we have, so that's x to the n, that's e to the x, and that's 1 over x. If we don't have something that looks like that, then we need to rewrite it, okay? So what we can do here, oops, a daisy. Is we can break this up into two separate fractions. So we can have x squared e to the x over x squared minus 2x over x squared dx. Okay? And now that we have that, we can see that some things cancel out a little bit, which is pretty nice. So we can cancel the x squareds, and we can cancel these x's. So then that gives us integral e to the x, just e to the x, minus 2 over x dx. Okay, I still want that to be in parentheses. And we can split this guy up into two separate integrals. So we have integral of ex dx and 2 over x dx. Now we have two integrals that look exactly like our integration rules. And so we can just apply those and we'll be good to go. So we have just e to the x, because that'll always just be the same, minus 2 natural log absolute value of x. And then we've said before that when you have two integrals, you can just combine their constants, since their constants are arbitrary, into just one constant. So we can just put plus c for both of them. Okay, so hopefully that clears up this problem a bit. That's really all it was asking for, was just to evaluate this indefinite integral. And really the key here is this step here. That's kind of the key step there. So I'd say once you have that step, you should be good to go, and everything else should be pretty clear. But if it's not, absolutely shoot me an email and let me know if you still have any questions. So the next problem that I got a request on, and I saw a lot of people did miss this one, was quiz 17 problem 2. Now hopefully I did see some people reached out to me before they retook the quiz, or before they took their second attempt. They actually reached out to me and asked me how to do this problem, but for anyone that might still be confused, I wanted to go over this really quickly because I did see it was a very missed problem. So we are told that this is the weekly marginal cost, and remember, way back from 9.7, marginal means derivative. So we have the marginal cost, and this is from 12.2, sorry, and our c of x function, that's cost in dollars. So we want to find our cost function if our fixed costs are $2,000 per week. I'm going to write that down. So we have fixed costs equal 2,000. Okay, and we're going to use that later. Put in the dollar sign. Okay, so first and foremost, we want to find our cost function given this marginal cost. So marginal cost is our derivative and cost is our original function. So to get rid of that derivative operator, to undo that, we need to take our integral, because integration like undoes a derivative. So maybe I'll write that over here. Undoes. We'll call it good. Okay, so we have that, and then we can put over here integral of what the actual function is, 12 plus 500 over x plus 1 dx. Now over here we're taking an integral of a derivative, so we'll just get the function itself. So we'll have c of x. And then we'll still have our integral over here, same as before. Okay, cool. So now we want to break up this integral into two parts. Because we have this x plus 1 in the denominator, we know that we're going to have to do a u substitution. And if we're doing a u substitution, we need to break up an integral into its smallest parts. So we're going to have 12 dx plus, I'm just going to move that 500 out, integral 1 over x plus 1 dx. Okay, so I kind of already said it, but we're going to want our u to be that x plus 1 because that's in the denominator. So we're going to have u equals x plus 1 and du equals 1 dx. So now we have that this guy is u and this guy is our du. So we can say we're still going to keep this guy as 12 dx, and I apologize if I'm talking fast. The last video I recorded ended up being way longer than I expected, so I don't want to keep you guys too long. Okay, so 12 dx plus 500 integral 1 over u du. So when we break up those integrals, it allows us to have two integrals with two different integration values. So here we have x and here we have u. And it'll still work out the same way, which is really nice. So now we can just treat this like normal. So we have 12 dx, so that is 12x plus 500 natural log absolute value of u plus c. And we can just group that c in for both of them. They can just be the same value. Okay, and our last step is just to plug in our u. Okay, and we are good to go. And then this is our general cost function. Now we want our cost function where our fixed costs are $2,000. Now this isn't something that's been, explicitly stated in this class, but we can kind of look at the word itself, fixed cost. Fixed being something that doesn't change, doesn't vary. It's a static value, okay? So what that means is we're looking at a value that doesn't depend on the number of items produced, or in this case, doesn't depend on x. Which value in our cost function doesn't depend on x? Well, maybe you can see it, hopefully you can. It's our constant. This constant here doesn't depend on our x. So what that means is our constant is our fixed cost. So fixed costs equals c, our constant, right there. Okay, so what that means is that our cost equation, all we have to do is rewrite it with that fixed cost value of $2,000. And that's all that is asking for. So when I went in and looked at some people's quizzes, that was the main thing that I saw that people missed, was solving for that constant. That's all that was asking for, was it was asking you to solve for the constant. Okay? But for the most part, I saw that the rest of you guys were kind of doing the integration correctly. It was just the constant that was incorrect. So hopefully that cleared that part up. And then the other piece that I was asking for was the average cost per pair of shoes if 1,000 pairs of shoes are produced each week. So to find that value, we remember what average cost is. So average cost is our C bar of X, that's that guy, which is our cost function over X, over the number of items produced. So in this case, we'll have C bar of X equals C of X for X, which is 12X plus 500 natural log of X plus 1 plus 2,000 all over X. And I'm really just going to leave it like that. I'm not going to try to simplify that function because it doesn't simplify super nicely. So now that we have that value, it's just asking for the value of this function at 1,000. That's all it's saying here. So we want C bar at 1,000, which is 12 times 1,000 plus 500 natural log of 1,001 plus 2,000. About to run out of room. All over 1,000. So when you plug that in, you should get about 17.45 as your average cost if 1,000 pairs of shoes are produced. Okay, so I hope that clears up any question you guys might have had over that problem. Okay, but if not, please email me. So the last thing that I wanted to go over was some problems from 12.4. So I just think that these problems touched on some really important concepts that I didn't have a chance to go over in Tuesday's discussion, so I wanted to go over them briefly today. But you could have chosen any range of these problems. I picked 2 of them, so problems 45 and 49 are the ones that I'm going to look at. So we are given these 3 integral values, and using those 3 integral values, we're going to evaluate several other integrals using integration rules. That was just integral and integration said a lot of times. So first and foremost, we don't have, looking at this problem, none of these functions up here look exactly like what we have here. But we have seen time and time again that we could rewrite this integral. So let's do that. Let's rewrite this integral. So we have 5x dx plus integral 1 to 4 x squared dx. Okay. And then lastly, I'm just going to pull that 5 out of there. X dx plus integral 1 to 4 x squared dx. Okay, well, we see here that for 1 to 4 x dx, that's 7.5. And then for 1 to 4 of x squared, that's 21. Okay. So we can actually just plug those values in. So we get 5 times 7.5 plus 21. And that gives us 58.5. Okay, so we were able to evaluate this integral right here without really doing anything with it, just by using this information we were given up here. Okay. So that's just a really nice handy skill to use. So now let's look at another problem that is really similar to that, but we're going to use different pieces of information about integrals. Okay, so here we have 6x squared from 1 to 5. Well, first off, none of our integrals that we are given go from 1 to 5. So let's use an integration property that tells us that we can break integrals up we can break our integration interval up into little sub-intervals. So we can break this up to 1 to 4 6x squared dx plus 4 to 5 6x squared dx. And if you want to know what that property is, you can go look at the notes from 12.5. I have that integration property in there. So we can do this anytime we want to, okay? As long as these two numbers are the same, we can do that. Okay? So, every time. So now that we have that, we have something that looks a little bit more like what we have seen, what we are given, but not quite, okay? So the next thing I'm going to do, I'm going to move that coefficient outside of the integral. So we get x squared dx plus 6 4 to 5 x squared dx. And now we have stuff that looks exactly like what we were given. So we have that this guy, we're told that that is 21. And we have that this guy here, well, that is 61 over 3. So we can just plug those numbers in. So we get 6 times 21 plus 6 times 61 over 3. Okay, well, this 6 and that 3, that'll simplify a little bit. So we can do times 2, and you can just plug this into your calculator. But I'm trying to do mental math, keep the brain sharp while in quarantine. So here we should have 126. So for this one, we should get 122. And then when we add those two together, we should get 248. Okay? So those were kind of the main 4 things that I had wanted to go over. This isn't a very comprehensive review, as you can see. One last thing that I would say that I kind of included in the announcements in the 12.5 video, but the exam is just over chapter 12. It's not a comprehensive exam, okay? It's not a cumulative exam. So it's just over chapter 12, but remember that anything that's included in chapter 12 is fair game. So you'll still need to remember derivative rules, and you'll still need to remember like cost, profit, and revenue and that kind of stuff, because that stuff is still fair game. But everything else, elasticity of demand, limits, all of that kind of stuff, implicit differentiation, that isn't going to be included on this final exam. It's just chapter 12. Okay? So that was everything that I wanted to go over. I hope you guys are still doing really well, and I hope your finals week is not horrible. Hopefully it's pretty manageable. But if you do run into any speed bumps along the way while prepping for this final exam, please reach out to me, and I will gladly get back to you as soon as I can. I will say that my finals week is pretty horrible, so I can't promise a super speedy response, but I promise it will be before Wednesday at the very least. So have a good rest of your day, and good luck on your finals.